Hi everyone, thanks for the nice introduction. So this is joint work with Anthony Leverrier, Alain Sarlet, Mazir Miarimi, and Christophe Vuillot. All right, so in recent years, starting from the Google experiment of 2019, various groups have been trying to experimentally demonstrate the advantage of quantum machines over their classical counterparts. So those were all amazing experiments in themselves, but unfortunately for many of them, they're eventually followed by someone coming up with a classical algorithm solving the particular instance that was considered in a similar amount of time. So there's some kind of ongoing competition between quantum and classical, and in this context, we'd like to have something with better guarantees, to have a quantum advantage claim with better guarantees. And to do so, we'd like to base our claim on a parameter with the following properties. So the first two properties are pretty obvious. So we want something that is classically hard, but quantumly easy. Whereby quantumly easy, I mean something that is not only solvable in polynomial time, but also on a near-term quantum computer, so with additional constraints on the number of qubits, the number of gates, and the connectivity. On top of that, when we're going to implement this on a quantum machine, so in the near term, this quantum machine is going to suffer from noise, and we're not going to get the exact solution, but some approximate solution. So in general, solving a problem approximately can be way easier than exactly, and we do not want that for our classical computer. So we want some additional property of robustness to noise. So this is of course going to depend on the implementation. And finally, we would also like to be able to verify the output of the quantum computer efficiently using a classical computer. Okay. So unfortunately, we don't know any class of problem as of today that verifies those four properties, and up until now, people have been mainly focused on something that verifies those first two properties, something that is classically hard and quantumly easy. And a good class of problems that verifies this is the one of sampling problems, which I'm going to define a bit later on. And essentially, what we have been doing in this work is taking a sampling problem and making it robust to noise with as little overhead as possible. Okay, so what is a sampling problem? So if you're given the classical description of a quantum circuit, you can associate to it a probability distribution that corresponds to individually measuring qubit at the end of your circuit. So then if you are given families of circuits Fn on n qubits, you can define the following computational problem that is going to sample from the probability distribution associated to circuits randomly taken from those circuit family. And that being said, if you choose your circuit families well enough, you could hope to have some classical hardness. And this is something that actually holds for some well-known families of circuits, of random circuits, such as boson sampling, IQP sampling, and random circuit sampling. And for those families, in the end, you're going to have some hardness results that state that it is hard to sample from those probability distribution up to constant error and total variation distance. Okay, so here you have some notion of approximation. You are allowed to you are allowed to some constant error and total variation distance, but is it enough to cover some realistic error model? Well, unfortunately, the answer is no in general. So if you're given a circuit of volume V, that is the number of qubits times the depth. For realistic error model, errors are going to typically occur at every space-time location of your circuit. And if you start from the ideal probability distribution P, then you can define the noisy probability distribution P epsilon that corresponds to the measurement output at the end of the noisy circuits. And the problem here is that the total variation distance between the ideal probability distribution and the noisy one can in general increase as high as V times epsilon, so the volume of the circuit times the error parameter. So of course the problem here is that you wanted something for the parameter to be classically hard that is below some constant, and here you have something that can increase with the number of qubits. So this means that you do not have any insurance that you remain in the quantum supremacy regime, and that to some extent a classical algorithm could exist that sample from those circuit families, from those noisy circuit families. And actually there was this beautiful paper that was presented last year at QIP that constructed a polynomial time classical algorithm that approximates sampling from some family of noisy random circuits. So which is a particular family, but still that hints towards the necessity to add some level of error correction to be able to retain some classical hardness. All right, so in our work, we have been focused on sparse IQP sampling, which is a subclass of IQP sampling, which corresponds to sample from circuits that are diagonal in the computational basis, where qubits start and are measured in the Hadamard basis. So for the sparse variant, essentially the diagonal circuits is randomly generated from T and CS gate with the following rules. So for every qubit, you apply a 1 qubit gate that is randomly taken from some power of the T gate. And for every pair of qubits, you apply a 2 qubit gate that is with probability log n over n that is randomly taken from some power of the CS gate. So all of those gates commute, and so they can be efficiently parallelized to some extent, and this gives you typically circuits that are going to be diagonal, but also of log n depth. So what is interesting with sparse IQP sampling is that, and IQP sampling is in general, is that it is a model of computation that is non-universal because we have only diagonal gates essentially. But on top of that, it is also non-Clifford. So because we have T and CS gate, and hence you can hope for some classical hardness. So this is actually the case. So we have the same kind of classical hardness theorem that I stated earlier that say that it is hard to sample from ideal average sparse IQP circuits up to constant error and total variation distance, where we assume two complexity theory conjectures. The first one that is common to every sampling problem, that is that the polynomial hierarchy is infinite. And the second one related to, that is specific to IQP sampling, and that is related to some average case reduction of computing the partition function of the Ising model. So once again, with this kind of results up to constant error and total variation distance, we don't really know if these kind of things can be extended to cover some realistic error model. And so essentially, we're going to try to add some level of error correction to this scheme. Okay, so in general, you can sample, like in theory, you can sample arbitrarily close from the ideal probability distribution using general tools from quantum error correction and fault tolerance. However, those come with a high overhead, and we do not expect quantum machines in the near term to be able to implement them. The thing here is that IQP sampling is not a universal model of computation, so we can circumvent some no-go theorem of quantum error correction by taking advantage of this specific structure, by taking advantage of those commuting gates. And so in particular, in our work, we try to not use any distillation and to limit the number of rounds of measurement and feed-forward to a constant. Okay, so let me summarize our contribution now. So essentially, if you're given some sparse IQP circuit that is going to be on n qubits and of typically depth log n, and some precision target in total variation distance, what we're going to do is build some mapping that is going to give you some intermediate, what I'm going to call an intermediate term fault tolerance sparse IQP circuit that is going to sample from the initial probability distribution delta close from the delta close in total variation distance. So saying it like that, it's just some kind of threshold theorem, but what is important is what this circuit actually looks like. So it is on the right of the figure, and essentially what is important is that it is a circuit that is of constant quantum depth with a single run of measurement and feed-forward. And at the end, like with classical post-processing, we sample from arbitrarily close from the initial probability distribution. Okay, so now let me describe a bit what this circuit is doing. So essentially, this is an uncoded version of the sparse IQP circuit on some new quantum error correcting code that I'm going to define a bit later on. So the first part of the circuit, the blue square, corresponds to preparing the uncoded plus state of this new code in constant depth. The red part corresponds to implementing the T and CS gate of the sparse IQP circuit, both transversally and in constant depth. And finally, the last part corresponds to doing the logical measurement, so doing the logical X measurement of the sparse IQP circuit. Okay, so yeah, there are some problems with the slides, but essentially what I want to focus here is on the red part of the circuit. So the middle part, and so what I want to explain is how we're going to start from a circuit that is of log n depth, and how are we going to reduce the depth on top of making it fault tolerant, so which is quite challenging. And essentially to do so, we're going to combine two IDs from two different quantum error correcting codes. That is that if we want to implement a gate in a fault tolerant manner, essentially the best way of doing it is doing it transversely. Fortunately, there's a code that has a transversal TNCS gate, and this is the 3D color code. But on top of that, we want to implement them in parallel. So to do so, we're going to use some properties of a repetition code. And I'm going to explain in which way we're going to combine those two a bit later on. But let me first explain very briefly what is the 3D color code, so that you understand a bit the figures. So essentially, a 3D color code is a 3D topological code, that is to say, a code that is defined on some 3D lattice, where you assign qubit to vertices, X stabilizers to cells, and Z stabilizers to plaquettes to define a CSS code. And if you add some additional constraints, you have a 3D color code, which has the interesting property that it has a set of transversal gates that includes the T gates and the CS gates. So essentially, that includes the sparse IQP gates gate set. So now, if you implement the sparse IQP circuit on this code, you're going to have something of log n depth, because you did not increase the depth of the circuit by doing so, but you did not reduce it. You didn't reduce it either. And so we're going to need some kind of parallelization. So the central idea here is that on a repetition code, you can implement phase gates in parallel. Since like a phase gate on a single qubit, on a physical qubit, corresponds to an uncoded phase gate on the repetition code. And if I translate this fact to the IQP setting, this gives us that if you start from uncoded plus state of a repetition code, that is to say GAG state, and you're able to implement T and CS gate, then you can implement a sparse IQP circuit in depth 1. Okay, so of course this naive approach has some limitations. So the first one is that when you're doing this, you're not doing anything against errors. So you are doing exactly the same amount of errors, but in a shorter time and across a higher number of qubits. And on top of that, of course, you are transferring the problem to the preparation of GAZ state, which is to some extent difficult, especially if you want to do it in constant depth, because you have some no-go theorem that I'm going to talk a bit later on. And which basically prevents the naive approach of just trying to concatenate a 3D color code and a repetition code. Okay, so now let me explain a bit how we're going to combine those two codes. So essentially, what we're going to combine them using some lattice surgery IDs. So this new code is called the tetrahelix code, and it is obtained by merging 3D color codes on the faces in lattice surgery language, which essentially corresponds to, I don't know if we see very well here, but which essentially corresponds to adding some new Z stabilizers that correspond to pairing qubits in some external faces of the two codes. And once you have done that, you're going to need to modify a bit the X stabilizer so that everything commutes and you indeed have a quantum code. But once you have done that, you can repeat the operation an arbitrary number of times. And if you arrange your tetrahedra in some particular arrangement that is called a tetrahelix, you're going to define the K tetrahelix code if you started from K tetrahedra. So this is not, strictly speaking, a concatenation of a 3D color code and a repetition code, but what is essential here is that nevertheless it keeps the two desired properties that you wanted to have. That is to say that implementing a T gate and a CS gate on a single tetrahedron of the chain is going to correspond to an uncoded T and CS gate. And so if you apply those on several tetrahedra of the chain at the same time, you can apply them in parallel. Okay, so now I said that the problem with this kind of approach is that you need to prepare the state. So here, once again, I wanted to focus on the blue part of the of the figure, so essentially the preparation of the state. And this is difficult because, for example, for GHZ state, you have some no-go theorem that states that if you want to do them with unitaries, you have some log n depth lower bound for preparing them. So you cannot do them in constant depth, and on top of that, this is not going to be fault tolerant because typically you're going to have errors that are going to propagate through your CNOT gates. You can also do them, prepare them using measurements. So essentially you start from tensor product of plus states, you measure Z parity across neighbors, and you apply some appropriate correction. The problem is that if you have some measurement errors, this is not going to work. So you're going to need to add some level of redundancy by repeating measurements, but this is going to increase the depth of the circuit. And so I'm going to explain now how we can circumvent those two things with the code that I defined earlier. So essentially, if you want to prepare the plus encoded state of a tetrahelix code, the challenge here is to do the merge step in constant depth, because we already have some result on preparing plus state of 3D color codes, which more formally corresponds to the single-shot preparation of 3D color code plus states. So let's assume we are given some 3D color code plus states. We want to do this merge in constant depth. So to do this, we're going to need to measure those new Z stabilizers. And what makes it work is that actually what we are looking for when we are doing this is essentially to measure the encoded Z parity across the two tetrahedra. And what makes it work is that the logical Z in a 3D color code is string-like, and we are measuring it across a 2D surface. So I drew some different ways of reconstructing these operators in the figures, on the blue one and the yellow one, but you have some others. And so what you are doing here is essentially going from some time redundancy that corresponded to repeating your measurement to some space redundancy that corresponds to measuring the same operator but at different locations in space. And so more formally, the classical problem that you're going to need to solve when you're going to do this measurement to correct your measurement errors is going to be to decode a 2D color code on the external border of the two tetrahedral code, on the two 3D color codes. All right, so now we have prepared our state in constant depth. We have applied our gates transversally and in parallel so that the sparse IQP circuit is in constant depth. And so we only have to do the logical measurement in the end. And since we have some non-zero threshold that essentially derives from some general results on LDPC code, then we can sample arbitrarily close from the ideal probability distribution by increasing the distance if we below some threshold. And so this corresponds to some classical post-processing at the end of the circuit. All right, so let me summarize a bit what we have been doing now. So we started from some non-universal sampling problems that nevertheless exhibit some computational hardness, classical computational hardness. Since this is non-universal, we have been able to design some tailored quantum error correcting codes where we are circumventing some no-go theorems of quantum error correction, such as Easton-Near theorem. And then, when implementing this sampling problem on this specific code, this yields a simplified fault-tolerant implementation that is essentially of constant quantum depth and polylogarithmic space overhead, and a single round of measurement and feed-forward. Okay, so here are some maybe a bit technical open questions, but maybe more essentially, another open question that I would add is to ask, to some extent, this kind of scheme is practical, and this is something that is going to, of course, depend on the physical platform. That's something I'd be happy to discuss with you guys. Thanks for your attention.
Great. Thank you very much for that really nice talk. We have time for a few questions. Okay, I can't see any right now, so I have a question maybe to start with. So You mentioned earlier on that you need to be below a threshold for this to work. I was just wondering, is it clear whether the threshold may be different actually for this very simple, restricted problem you're trying to solve than sort of general fault-tolerant quantum computing?
No, I don't think so. You would get a different threshold. Essentially, you would get the threshold of a 3D color code if you directly apply this approach. Then I know that there are some proposals to go to a higher threshold by implementing some, instead of doing error correction, doing some post-selection things. I don't know if you could directly apply this to this scheme, but maybe that'd be an interesting direction to look for. Yeah.
Okay. Cool. Okay. Do we have any further questions? Okay, well, if not, I guess we're sort of heading towards the first coffee break, so maybe we can just thank Louis again and